Luca, and today I'll talk to you about optimizing parallel for loops in Cilk using loop frames, or in other words, how to make parallel loops run faster. There's been enormous economic growth due to faster computation, enabling us to process giant data sets more and more quickly. However, growth in hardware speed is slowing down. In this diagram, you can see clock speed in blue has plateaued around 2005. We can think of clock speed as an approximate measure of how many lines of code are executed per second. And in order to maintain growth, we need to turn to performance engineering and parallel programming. Think of it this way. If we can't execute code faster, we need to either split it in between multiple processors or reduce the size of our code. Indeed, the number of processor cores started growing around the same time. Unfortunately, parallel programming is hard. Let's say we have a task that requires a certain amount of time when run on a single processor core. Ideally, when we run it on 8 processor cores, we'd want it to run in 1/8 of the time. This is called perfect linear speedup because the speedup scales linearly with the number of cores we have. However, in practice, there's always some overhead represented by this orange triangle as a consequence of synchronization in between those processors. As researchers in this area, we want to build tools and improve them to help programmers get as close as possible to perfect linear speedup. Now let's talk about parallel loops. Parallel loops are the heart of parallel programs, and they're currently scheduled using divide and conquer, meaning they're split into halves recursively all the way until small batches, which are then executed by the processors. This implicit binary tree that the process has to traverse results in overhead, which we've seen on the previous slide in orange, results in suboptimal performance, and not much research discusses ways to mitigate it when it comes to parallel loops. That's why I'm introducing the loop frame, a very compact data structure that represents a loop with only 2 variables, start and end. Preliminary results are very promising. In the spring, we implemented a simple prototype of loop frames using mutual exclusion. Shown here in red, we can see that it achieves an almost 2x speedup over the existing divide and conquer shown in yellow. This semester, using a better synchronization protocol shown in blue, we achieved an almost 3 times speedup compared to divide and conquer. Parallel scalability of all 3 implementations is extremely similar, meaning that as we increase the number of processors, the speedup scales similarly for all 3. Because we're modifying an underlying implementation, this means our speedup can be applied to existing code that doesn't need to be rewritten, and means that our parallel loops are getting closer to perfect linear speedup. Thank you.